Welcome everyone to our inaugural first Digging Deeper We Count speaker series. And the We Count project is a project of the Inclusive Design Research Center. And there we are looking at how do individuals that are not part of the majority, that are potentially small minorities and outliers fare, especially individuals with disabilities fare within data-driven decisions and artificial intelligence. So we're looking at the data economy, both from a perspective of how do individuals with disabilities participate, but also how are individuals with disabilities treated by AI systems. And today we're honored to have Toon Calders, who's a professor in mathematics and computer science at the University of Antwerp in Belgium, sharing his work with us. Dr. Calders' research interests include quite a number of things, including machine learning, pattern mining, entity resolution, and of particular interest for We Count is discrimination and fairness-aware data mining and data streaming processes. He's published more than 60 papers in the data mining area, including 17 journal papers in high-level data mining venues. And of importance in this webinar and relevant to We Count is that, and one of the considerations we hope that he will give us some insights in, is that in systems based on data and data mining, we often have decisions made from biased data. Recognizing the occurrence of bias, discovering how bias is introduced and amplified, and removing these sources of bias is necessary for equitable and inclusive systems. And today, Professor Calders will introduce and motivate research in fairness-aware data mining. I'm very much looking forward to hearing more about this work. Welcome, Professor Calders.
Thank you. So let me
And Vera, you should stop sharing your screen.
Voila. Can you see my screen?
Thank you, yes.
All right. Voila. Do machine learning algorithms reinforce stereotypes? That's actually the main topic of my talk. And the title of my talk is Machine Learning Discrimination, Bias In, Bias Out. So this is already an indication that machine learning may actually reinforce some stereotypes if biased data goes into the machine learning algorithm. Now, before we go into that topic, let's first define machine learning. And this is the definition of Bishop, who is the author of a very important book on machine learning, and who defines machine learning as building a mathematical model based on sample data, as examples, let's say, that are known as training data, in order to make predictions or decisions without being explicitly programmed to perform the tasks. So let me give an example of that. So what you see here at the bottom left are 100 thumbnail images that are categorized into 10 categories, ranging from airplane at the top to truck at the bottom. And this is a very well-known benchmarking data set for image recognition. So basically the task is to learn, and that the computer can learn to recognize what is this being displayed on the different images. In order to do that, machine learning will learn a mathematical model and based on a number of examples. In this case, there are 100 examples. In reality, there will be thousands of examples. And that mathematical model should enable us to label new examples. So here are 3 new examples. And so the first one is a car. We run it through our mathematical model, and then an automobile comes out. The second one, ship. The third one, bird. And so here in this case, we make 3 correct predictions. So that is what we try to do. And if we look at machine learning, how prevalent or how powerful is it, then for this particular task, we see that human performance is on average 94% correctly classified. And this is because, and these are small thumbnails, the resolution is very bad. So some of the images are really, really hard to recognize because of the low resolution. a human being can do about, let's say, 100 per minute. If you're really into it, you're really trained into it. So now let's compare this to what a machine can do. So in this task, machine performance, the best known model trained on this data is actually 99% accurate, much more accurate than a human, and can do thousands of images per second. So machine learning is a very powerful technique, and where we do not explicitly have to say, okay, now you need to look at the color of the pixel, or you need to compare two neighboring pixels, or there are certain regions of the image that are important. And the model is learned automatically by the machine in order to make predictions, and it can do that better than humans. All of you have been using machine learning today, and machine learning is used everywhere. For instance, your emails, to recognize whether an email is spam or non-spam. These are machine learning algorithms, models that have been trained on thousands of examples of spam emails in order to detect them. A route planner, what is the most optimal route, predicting how much traffic there will be on the route. Also the results of a search engine, automatic translation, or even in the government for tax fraud detection. So there are many, many applications of machine learning. So how is machine learning done? And let's look at a very simple example. And so machine learning is an algorithm, is a step-by-step procedure to find a good model. And the task that I have taken here is the one of recognizing whether a certain image is an image of a dog, a chihuahua, or an image of a muffin. And so it's for humans, it's not such a difficult task, even though the images are very alike. But for a computer, this is actually a rather difficult task. So the first thing that we need to do is we need lots of examples, and we need to describe these examples by measurable characteristics. So for instance, we could look at the images and we could count the number of round shapes. And we have a small program to count the number of round shapes, and we have the color intensity. Then we can put our images with respect to these characteristics. And now the model that we are trying to learn, and basically we try to learn a model that is optimally consistent with the input data that we got. So here in this case, we can learn a line, for instance, a relation between the number of round shapes and the color intensity. And here we see an example of a line that's not very good. And we have our images that are categorized according to the two characteristics that we have. And then we have a line separating positive images from negative ones. And then we see, for instance, that here this dog is mistakenly characterized as a muffin by our algorithm, while here this muffin is incorrectly classified as a dog. So we're trying to learn something which is optimally consistent. And so here on our training data, we made learn this separator. And this is a much better model, because now we're no longer making mistakes on our training data on the examples that are given. Because of this, once we have learned the model, we can actually apply the model. And if a new example comes, we measure the characteristics, the number of round shapes, and the color intensity. We apply our optimal model that we learned. And here we see that this is on the negative side of the decision boundary. And so this is characterized as a muffin. Voila. So many types of models exist. Here in this example, we had a linear separator, a line that separates positive from negative examples in a numerical space and two-dimensional space. And these models, they come with a learning procedure, and this learning procedure will not blindly try out all possible combinations of lines, but instead of that, it will be based on model parameters that are being updated. So in our example, the parameters are the intercept and the slope of the line. And the update could be based on the distance of our positive and negative examples with respect to our decision boundary and whether or not they are on the right or on the wrong side. You could see it a little bit like a radio, an old FM radio, and you want to search for a station. As you turn a little bit to the right, a little bit to the left. If it starts cracking more, it means that you need to turn a little bit more to the other side, and until you get a good signal. And here something similar happens. We have our intercept and our slope, and we slowly change it in one or the other direction until we find a model that is predicting the class that we want to predict well. So here, the performance that we are getting on our training data is actually the signal that we are getting to stay in with this parallel with the radio. So machine learning has a very big promise, and because human decision makers, and they are susceptible to prejudice and bias, for instance, with respect to gender or racial stereotypes. While machine learning is free from bias, it's no longer based on our gut feeling, but on facts and statistics. At least, so it seems. However, if we look at models that are being used, let's look, for instance, at the model that we had in the beginning with this CIFAR dataset, the 100 images that we want to classify from automobile to bird or plane, etc. If we look at the models that achieve this 99% accuracy, this is not like a radio that has 2 or 3 buttons, and it is more like a cockpit of an airplane that has millions and millions and millions of parameters. So in this specific case, and the best performing model for this specific task, recognizing or classifying small thumbnails into 10 classes, if you have a book of 1,000 pages and this book is not big enough to write down the mathematical formula that is being used in order to recognize these images. So we're getting actually these kind of black box models where we do not know why certain predictions are being made. And to make things worse, these models may actually unintentionally pick up and amplify bias from our training data. So if our training data is biased in one way or another, we will also see this in predictions. And let me show you 2 recent examples of bias in machine learning, and to illustrate that this is actually a real problem in some situations. So the first example is that of word embeddings. And a word embedding is basically a representation of a word or a text as a vector of numbers. So for instance, here we have 3 words, banana, father, and baby, and we're making an embedding into 4 dimensions. So every word will be represented as a vector, a list of 4 numbers. So here, banana is 0.3, 5.8, 7.3, 0.1, and father and baby also 2 different vectors. Why do we want to do this? And why do we want to represent words as vectors? This is because if you look at the machine learning models, and they are mostly based on numbers and doing calculations with these numbers. For instance, our images in the beginning, our 100 images in 10 classes, these are pixel values. And so this is basically a big list of numbers that in which we can represent our images. And that's easy for our algorithms to work with. Text is notoriously hard to work with because we cannot do calculations with it. We cannot say 2 times the word minus 5 needs to be larger than 10. But if we go to this type of representations, we can actually do calculations and we can fit it in our normal machine learning models. So people have been exploring ways to make embeddings of words into a multidimensional space. And these embeddings, they usually have the properties that if they are used in similar contexts, then they should have similar vectors. So let me illustrate with an example. Suppose we have words and we can divide these words, and these are adjectives. We can divide them into, or we can put them on 2 axes. You have the horizontal axis, which represents whether this is a word that is more about people, or on the left-hand side, words that are more about food. And we have the vertical axis, which represents that a word is more positive, or a word can have a more negative connotation. And then you see how we can put words onto this axis, and a word like intelligent and trustworthy. And these are words that we usually say about people and not about food, and have a positive connotation. Dense or obnoxious. A person can be obnoxious, but a banana usually is not obnoxious. And so this is scores high on the horizontal axis, but is actually a negative word. Words that are more about food, like tasty, a positive word about food. And so this ends up in the upper left corner. And so in this way, we can basically, voila. And what is now the crux of this type of techniques is that these vectors, they are usually learned from example documents. So it's not a collective of people that take the dictionary and now start dividing them up into different categories and start giving them coordinates in a multidimensional space. No, these things are automatically learned from example documents. For instance, the company Google has done machine learning and has trained algorithms in order to divide words or to give positions to different words, or to give coordinates to these words, and they are freely available online. You can download them and you can use them, and you can use them as some kind of connector. And so you get a text, then the words of this text, you can look up for each word what is the vector that is learned for this word by machine learning, and then you can apply your favorite machine learning algorithm. And these word embeddings, and they're really great because they truly capture semantic information about our words. So here, what you see, and I will enlarge it a little bit, the one on the left. So what you see here is a two-dimensional embedding of different words. And in this case, we have here slow, and then we have the different comparisons of these words. So we have the comparative, slower, and then the superlative, slowest. And you can see the position of these words. Now, these positions, they are learned automatically by an algorithm by the way that they are used, the context in which they are being used. Similarly, we can see the vector for short, shorter, and shortest. And one thing we can see is that this algorithm actually captures semantic information, because if you look at the difference between slow and slower, and that's this vector, this is more or less the same as the distance between short and shorter. Similarly, between the comparative and the superlative, if you look at the difference between slower and slowest, and shorter and shortest, that's more or less the same vector, and so their relative position is more or less the same. So this means that, suppose that I have a word, slow, slower, slowest, I know the positions of these words, and now I have another word, short, and I do not know what is the comparative and the superlative of this particular word, then I can look at the words for which I know this relationship, slow and slower. I can basically look at the relative position of these two words, and I can apply it here, and I can find that shorter is a comparative of short. Similarly, if I need to have the superlative, then I can again look at the difference between slower and slowest, take this difference and add it to shorter, and I will get a position which is close to the position of shortest. And so this allows us to infer a lot of semantic information about our text, and to actually turn it into numbers that our algorithms can understand. A similar thing here on the right-hand side, a similar thing happens if you look at male and female versions of words. And the difference between male and female is, for instance, very similar as the difference between king and queen. And so in this way, we can even make comparisons. If you look at the difference between the words man and woman, that's more or less the same as the difference between king and queen. We can also look at countries and capital cities. France relates to Paris, like Belgium relates to Brussels. Singular and plural, apple relates to apples, like king relates to kings. So in this way, we are actually capturing a lot of semantic information. And this has great applications. And so here you see a two-dimensional representation of sentiment analysis. And so these are actually short messages, and we want to know whether the message is positive or negative. And in order to do that, we compute the positions of the different words, and we represent each text by the mean position of the words that are in this text. So here you see, and there are two dimensions, horizontal and vertical. The blue dots represents negative texts, or texts that have a negative connotation, negative sentiment, express a negative sentiment, and the red ones represent a positive sentiment. And there you can see that the red are more to the right, and the blue ones are more to the left. And so basically we can learn a separator that separates positives from negatives, and it will be better than random. If additionally we use some other characteristics of our text, and we can even improve the performance of our texts. So this type of technique, this type of representation is, for instance, used by a professor in our university that uses this to recognize from messages on Facebook whether they are connected to cyberbullying or not. And because there, the positivity or the negativity of a message is very important. And so there are really nice applications, and it's very important that the position of our words actually capture the semantic interpretation of the word, or the semantic information of the words. But, and this is the backside, these representations, they also capture cultural bias. These representations, they are trained on, and so to the original ones, they were trained on news articles. And so they also learn some cultural biases that are present in this text. So in one paper, and the authors were looking at, so let's look now at our representation, and let's do this analogy. And so we take the difference between men and women. And so let's now see a computer programmer, at least in Belgium, is a typical male profession. So let's now see what is the female variant. And so people that have so females, if they're not computer programmers, and what is the profession that is connected to that. And then it turns out, if they run the algorithm and the word embeddings, that the word that is closest to make this equality true is actually homemaker. So, and this is kind of insensitive of this algorithm, but the algorithm is not trained to be sexist, but this is a result of the fact that it has been trained on news articles, and then women are in these articles apparently the difference of the way that men and women is being used is the same as the difference between computer programmer and homemaker. And there are a lot of other gender stereotypes that turn up in this data set, and like the male version of sewing is carpentry, female version of a surgeon is a nurse, etc., etc. And so these are these. Is this harmful? Yes, I think it is. Why is it problematic? And because these type of techniques, they are also being used, for instance, to develop techniques that screen your CV to find the perfect job for you. And so there is also automatization going on in these areas of research. And then, of course, we do not want to have this type of gender biases inside our decision procedures, and we do not want them to be reinforced or even made permanent by our machine learning algorithms and automatic decision procedures. Here I did some research myself, where I looked up ethnic names. And so I looked up the 10 most popular black names and the 10 most popular white names among males and females. And then I compute the distance of these names to different words, like, for instance, criminal, gun, smart, etc. And then you see that there are huge differences between them. And for instance, let's look at the word criminal. If you look at the distance, these are male names and these are female names. The average distance here is or the average similarity is larger for male names than for female names, for instance. And so here you see some racial and gender stereotypes being reflected in the representation. And this is, of course, not desirable. So that's our first example, and where our input data is clearly biased, resulting in a biased decision procedure. So let's look at a second example, and this is a very well-known example, which is called the COMPAS. And COMPAS stands for Correctional Offender Management Profiling for Alternative Sanctions. And this is a risk assessment tool that is used to predict, among others, the risk of recidivism. And so the label that is being used and the data on which this is trained is data from people that has had to appear in front of the court. And then the label was given to our training data, whether or not there was an arrest within 2 years. Very similar as with the images. And so basically they want to learn a risk scoring model that predicts for a new person that arrives, whether or not he or she will commit a crime within 2 years, and whether or not there will be a new arrest within 2 years. Data that is being used as inputs are, for instance, pending charges, prior arrest history, previous pre-trial failure, residential stability, substance abuse, and so a lot of attributes that are correlated with criminality. And this data or this tool, the decisions that were generated by this tool were analyzed by a consortium of investigative journalists called ProPublica. And after studying the data and the predictions that were made by this model, they actually came to the conclusion that the algorithm that was being used there is racist. This study showed, for instance, and here you see a table where we see errors that are being made by the model. And so basically what did ProPublica do? They looked at one particular state and people for which this risk model was being used. And by asking for the data, and they actually received the risk scores that those people received by the tool. And then they could compare this to what these people actually did in future. So they could look at 2 years later whether or not they committed another crime or not, and then they could compare it with the risk label that was given. And so we have a certain point in time when the score is being computed by our tool. This score has been released and ProPublica has access to it. But since the score was given, 2 years have been passed. And so 2 years have passed since then. And so ProPublica and the journalists, they could look up for those people whether or not they recommitted a crime. And so they can see for which people an error was being made. And an error could be that you were labeled high risk, but you do not reoffend. Or you could be labeled low risk and you did reoffend, but you did reoffend nevertheless. And so now if they look at the white or black defendants, they see a huge difference in errors there. Up to 44.9% of the African American defendants were actually categorized as a high risk but did not reoffend, while for white people, that was only half of that, a little bit more, 23.5%. And so there's actually a huge difference. So it's the COMPAS algorithm is overemphasizing the risk for African Americans is one conclusion. If you look at the opposite error, and so where someone got a more beneficial label than they deserve, they're labeled low risk, but they did recommit a crime within this 2-year period. And then we see that whites are much more likely to receive this treatment than black people. So So is this fair or unfair? And the conclusion of ProPublica was that this is clearly unfair. And many presentations actually stop there, but I actually like to add, because it forms a nice bridge to the next part of my talk, I would also like to add the defense of Northpoint, and that's the company that actually developed this scoring tool. The algorithm itself is unknown, and this is proprietary. Only the decisions had to be revealed to ProPublica. And what Northpoint says in their defense is, okay, maybe there are differences in the errors and how they are made among black and white defendants, but the scores are calibrated. Now, what does it mean that scores are calibrated? And for this, we need to look at the graph here on the right-hand side. And calibrated basically means that if I give assign a risk categories to someone, then the meaning of that risk category should not depend on the ethnicity of the person. So if I assign the label "you're a low risk" to someone, and then this means in their study, it means that this is someone who has a probability of around 30%. So this is what is on the vertical axis. This person has a probability of about 30% to commit a crime within 2 years. If you get the medium risk label assigned, it means that you're like around 55%. That's here. If you get the high risk category, and then there is up to 70% probability that you're going to commit a crime again. So here we see two bars, and this bar is on the left-hand side. There is the rate of committing a new crime for black people, and the other bar is for white people. And then what we see is that even though there is a slight difference, it's not that big, that the risk categorization basically means more or less the same for both groups. So their conclusion is our algorithm is not discriminatory, because if we divide people into risk categories, then black and whites are equally likely to recommit a crime if we condition on the risk categorization that they received. So how is this consistent with what ProPublica came to conclude? And this basically is a consequence of the following observation. So if what ProPublica did is they basically divided it into two categories, but this is not that essential in the analysis, but basically they divided into high and non-high. And so now they're looking at where are the errors being made. And so everyone who is in the high risk category, I'm going to predict you're a high risk. And everyone who's in low or medium risk, I'm going to predict you're not in a high risk category. So then the errors that are being made are in the high category. 70% of people are recommitting crimes. So 30% are not recommitting crimes. So of all those people that get a high risk label, actually I'm making an error for 30% of those people. And for these 30% of people, I'm making the bad type of mistake. I'm saying that they're high risk, and while they're actually not recommitting crimes. For everyone who is in the low or the medium category, I'm making the other type of mistake. For those people, that even though there is 55% of people that recommitted crime, I'm actually saying that they're not a high risk. So for 55% of those people, and so this bar here, I'm actually saying you're a low risk while they recommitted a crime. The people that are here, the other people, the other 45%, for them, the prediction is correct. In the low risk category, it's even more. It's 65%. I'm actually making the correct prediction, but for like 35%, I'm making a wrong prediction. So now what is the key observation here is that the errors that are being made in the low and medium category are always errors that are beneficial for the defendant. I'm predicting that they're not going to recommit a crime while they do for the green ones. And while in the high risk category, I'm always making an error which is not beneficial for the defendant. I'm saying that they're going to recommit a crime while they're not recommitting a crime. And so now it turns out that black and the black defendants are relatively more frequent in the high risk category than in the medium and the low. So they're overrepresented in those categories where these unfavorable mistakes are being made, while the white people are overrepresented in those categories where the good type of mistakes are being made. Well, good from the viewpoint of the defendant. And that's actually what this black line, and that I didn't explain yet, and the one here is showing. That's the relative number of black defendants that are in this category. So in the low risk category, it's like 50-50 black and white people, and while in the high risk category, it is like 80% black, 20% white. And so that is how it can be consistent, how a classifier can be calibrated, and at the same time there can be a huge imbalance in the type of errors that are being made for the two communities. So this brings us to the question, so what does it actually mean for a classifier to be fair? If we want to build classifiers, or we want to build machine learning algorithms that are fair, we first need to understand what it means. We need to find a formula that expresses, and so here are a number of examples, black and white defendants, for which we know whether or not they recommitted crimes, apply the scoring algorithm to it, and now there is an outcome, and we can say whether it's fair or not fair. And here in this example, ProPublica says it's not fair, and Northpoint says it is fair. It's just the way you look at it. Do you look at it from the calibration point of view, or from the type of errors that are being made? So a first attempt that we could take is, we could say, okay, the decision should not be based on ethnicity. So just remove ethnicity from our data set. And this is what is usually done. And this is probably also the case. I'm not certain, but Northpoint is probably not using ethnicity in its decision procedure. That would probably be illegal. However, then the redlining effect comes into play. And so what you see here is a small image of a map that was used by banks, where basically after it became illegal to look at the ethnicity of a person to deny or give a loan, they were actually starting to use maps where they would delineate certain areas in the city as being good neighborhoods, some areas as bad neighborhoods, and people that were from a bad neighborhood were much less likely to receive a loan. And so the redlining comes from drawing a red line around certain regions. And in this way, even though they were not directly using the ethnicity of a person, they could still discriminate. Here something similar happens. A lot of these attributes, they are correlated with the ethnicity of a person. So removing the ethnicity of a person will not help at all, because the other attributes, the other characteristics of the defendants do allow to make a very good prediction of the ethnicity of a person. So our first attempt actually fails. So let's try a second attempt. And so Northpoint and ProPublica have different visions, but maybe we can build another model that actually satisfies both Northpoint and ProPublica's definition of fairness. So let's translate them into human understandable language. So what ProPublica is actually saying is that if you deserve to be released, it shouldn't matter whether you're black or white. We do not want to see these differences between, if you look at people that did not recommit a crime, well, then it should be 20% blacks and 20% whites that got the high risk label, but it should not be 20 and 40 as it is now. On the other hand, they're saying also the opposite. If you deserve to stay in prison, it shouldn't matter whether you're black or white, and that you should have to stay in prison with the same probability. I'm not going to go into the formulas, but these definitions, we can write them down in a mathematical sound way, such that we can do derivations later on. If we then look at the Northpoint point of view, They're looking at calibration. So basically they're saying, if you look at the risk score that someone gets, what it means should not depend on your ethnicity. So there should be a universal probability of reoffending if you're in high risk category, and a probability of reoffending if you're in a low risk category. Again, we can write this down mathematically in a mathematically sound way. And so now we can analyze, can we make a decision procedure, a categorization into risk groups that satisfies both ProPublica and NorthPoint's definitions. And then it turns out that actually it's impossible to do this unless in very, very exceptional conditions. And what are these exceptional conditions? The first one is in case of perfect predictability. So the image here is of the movie Minority Report, where people are getting arrested even before they commit a crime. And if you have a perfect predictability, you could actually do that. It's another question whether it's ethical or not, but it means that you know on beforehand 100% certain if someone will recommit a crime or not. Of course, not very realistic. But if that is the case, well, then we can build a classifier that satisfies both, because we will not make any errors. So it's the errors will not be unbalanced between black and white. And on the other hand, it will be calibrated, because if we say someone is high risk, it's 100% certain that he will recommit a crime. If we say that he is low risk, there is 0% probability. It doesn't matter what your ethnicity is. So that is one case. And the other case is if there are equal base rates. So this means that actually both communities have the same recidivism rate. Now, in this particular case, this was not true. And the black defendants had on average a higher recidivism rate than the white defendants. So this is unrealistic. This is not satisfied. So in this particular case, we can say, okay, it's just impossible to satisfy both definitions at the same time. So what can we conclude from this? That there is no universal definition of fairness, but any definition will be situation dependent. And so here in this particular case, a legislator will have to choose between the interpretation of NorthPoint or the interpretation of ProPublica, but they cannot go with both definitions at the same time. So once we have decided, and so now this is the third part, and I'm kind of running out of time, so I'll go a little bit faster here, or I will shorten this last part a little bit. So how can we now implement this into algorithms? And suppose that we have chosen and we want to go with NorthPoint's vision, or we want to go with ProPublica's vision. We've decided one of them, and so now we want our learning algorithm to learn a decision procedure that is fair with respect to that criterion. And then many different methods have been proposed. Some of them alter the training data, which means, for instance, if we learn our word embeddings, to go back to our first example, we will not use news articles, but we will use more gender neutral text in order to learn our word embeddings. Or we can change our learning algorithm. So our learning algorithm was like turning these knobs on our radio until we find the radio station. And so the signal that we're getting is how good is our prediction. And so we can add to our signal not only how good is our prediction, but we can also add a penalty if we learn something that is very discriminatory. And so we add a penalty, and then we want to optimize the accuracy of our method. How good is it in prediction versus we're trading it off against the discrimination. And a last one is we learn the model. The model turns out to contain unacceptable bias. Then we can try to update the models. And so a good overview of the different techniques is in the paper that is given here. Then, of course, if you want to be fair, this comes at a price. And so here I just want to point out one particular case study that is given in a paper of Hart et al. In a NIPS paper. It's just a small part of the paper in the experimental section, but I find it very, very illustrative. So basically they are using the FICO score, which is some kind of score of creditworthiness of people, in order to divide people in deserving to get a loan or not deserving to get a loan, or whether or not a bank should give them a loan. And then based on this FICO score, they will decide this. Now, if you look at the FICO score and the distribution, the non-default rate, then what we see here on the left-hand graph, we see on the horizontal axis, the FICO score, and on the vertical axis, the non-default rate. So one thing you can see is the higher the FICO score is getting, if you're going to more to the right, the non-default rate is also increasing. So that is nice. So it means higher FICO rate means higher probability that you're not defaulting. For instance, here, if you get a FICO score of 600 or more, the probability that you're defaulting is less than 15%. And so this part here. Here on the right-hand side, we can see that actually this condition, this equal base rates that applied, and that this is not the case here. The distribution of FICO scores is very different for different ethnicities. So here you see the FICO score for Asians, and so it stays low. So there are very few Asians that have low FICO scores, and then for the high ones, it goes up. And so the highest probability mass is here. And then, for instance, for Black people, the FICO scores, and they're more equally distributed, so they are more likely to have low FICO scores. So then we can think of different scenarios, and we can see what happens to the profit. And so this is an imaginary case, and so they add some margins to it. If you give a loan to someone who doesn't repay it, it costs you some money. If you give a loan to someone who repays, you gain some money. So you can look at the optimal score. And the optimal score is obtained when you're doing racial profiling. You're putting different thresholds for Asian, white, Hispanic, and Black. And that is the max profit case, of course, illegal and unacceptable. If you apply a single threshold among all of them, and this is what the single threshold is saying, then actually our profit is diminishing a little bit, not too much, and that's because the FICO score is very well calibrated. If you look at the kind of rules that ProPublica is imposing, and the errors should be balanced, that is what is called equal odds, then actually a profit will go down to 80% if you're only looking at people that deserve to get a loan. And we're saying that for all ethnicities, they should get the loan with equal probabilities. And then in this particular case, the profit goes to 92.8% of the optimal one. So what is the takeaway message of this? And that if we're going to apply these fairness principles, and then this will come at a price, and that we will have a slightly lower accuracy in predicting our labels. So to conclude, machine learning models, they are not fair out of the box. If biased data goes in, biased data comes out. The example of our word embeddings, for instance. Fairness-aware data mining and fairness-aware machine learning research is looking at the problem, how can we build models that optimally avoid certain types of biases. One very important remark, and that was the ProPublica versus Northpoint example, is that, however, it's partially inherent to decision-making. Unequal base rates between groups provably leads to differences in treatment. Either our classifier will no longer be calibrated, or there will be an imbalance in the errors that it is making. And that means, and a last point, I didn't talk about it, but it's also an important point, I think, and that actually transparency of the models that are being learned is also a very important characteristic. Voila. So this was my presentation, and I'm now ready to take questions.
And while we're queuing up the question, actually, I want to butt in the line and ask you a fairly specific one, which is, you've given us examples of gender and race, which are often easily identified characteristics within a data set, whether it's the semantic text, the analysis, or a self-identification within data sets regarding demographics. The difficulty we have if you are a person that's experiencing a disability is that people are very, very diverse. And so the data characteristics are very, very diverse. In fact, the only common definition of disability is from a data perspective is that you are far from average in some factor that causes a barrier within the designs that you encounter in your life. So determining that there is discrimination, determining where the discrimination happens is extremely difficult, because even from the beginning of the data ecosystem, where you can identify or label data, create vectors, it's a very challenging task. So would you have any advice or comment on this particular challenge?
So if I understand correctly, the particular challenge is the fact that the data is relatively sparse, right? That the characteristics are very...
Well, the data is sparse, the clustering of the data, the identification that... So we know there is diffuse discrimination because of common patterns. The data is from the past. So let's take the example of employment. I'm applying for a job. There is an automated system that is used to filter out who's going to get an interview within a competitive process. Because there will never have been anyone within the position that has the specific data profile that I have, it is highly unlikely that I will make that list of 10 people that will be interviewed. However, my particular data profile will be unlike anyone else's. So there isn't a way to say, oh, well, this is like this other person who also has a disability. It won't be. The data sets aren't there to say that someone who is blind the data points will differ quite a bit from somebody, say, who has dyslexia or has experienced a combination of a whole range of different things which cause the systems that they're encountering within the employment to work or not work. So not only is it difficult to determine whether discrimination or bias has happened, or whether something, the system is biased against you, but to then determine a way to address it as well becomes very difficult.
Mm-hmm. Yeah, that's true. So I think this type of models, they actually should take into account two aspects of the decisions that they're making. On the one hand, the probability they are giving to a certain label, but on the other hand, they should also take into account uncertainty that they have in certain regions. So in this specific case, I would say that probably the use of some kind of exploit-like algorithms, where you actually sometimes give a positive label to some instances for which you do not have a lot of data in order to explore the label, could be a partial solution. On the other hand, what I also would like to add is that machine learning is especially useful in contexts where you have a lot of training data that allows you to build up a good mathematical model of reality. So here in this particular case, if you do not have sufficient examples of, for instance, people with disabilities, and whether or not they're qualified for certain jobs, then maybe you shouldn't be using machine learning algorithms in this specific context.
although, so that often that isn't the choice. The place you wish to apply to has chosen because they show that there is accuracy in terms of the prediction compared to human prediction. But if you actually analyze the pattern, it'll be highly accurate for average or typical applicants, but you are an anomaly, and therefore there is no data to support that you might actually succeed, and therefore you won't get the job. So there will never be data that you can succeed. And it's a vicious cycle. But I'm going to let the other questions, and I'd love to continue this discussion with you at some point.
Mm-hmm, mm-hmm. Yeah. Let me just say like that there exists a number of machine learning approaches and like Bayesian approaches that not only quantify the label that someone should get, but also the level of uncertainty attached to it. And so here, I'm not saying that this is like the golden bullet, but that is certainly something that you should take into account. And so there do exist techniques in order to detect that an instance that you're classifying is actually coming from a region that is sparsely populated, making that your prediction is less reliable. Yeah, but it's actually a very good point that you're making.
And this is part of what we're working on in the WeCount project.
Okay. Mm-hmm. All right. So how does it happen? Do I need to look in the Q&A and pick some questions, or is someone going to moderate?
So sorry, I lost my controls, Toon, and I wasn't able to. So I was suddenly scrambling. Just give me a moment, please. There are a number of really good questions, but we've come to the end of our designated time. So just before, if you have time to stay and answer some questions, that would be lovely. Am I sharing my picture of my kids right now? I'll just, I see, there we go. Put that. I just want to first of all say thank you, so that people have it. There's been many comments in the chat, people thanking you for being here today, and I also want to let people know to keep an eye on the WeCount website. We've got some more events coming up in this series, and any questions that we don't have time for today, Toon, perhaps we could answer them after the fact, and we'll post those on our website with the recording of the video of this presentation as well. So there were some questions. There's some in the queue right now, but we also had some earlier ones that were provided, and I thought this one sounded interesting. It's around debiasing. It was provided by Michael McKenna, and he was talking about most of the literature focuses on classification, and he was wondering, are there effective debiasing tools available for regression models? Is that something you're able to answer?
Yeah, that's a very interesting problem, and actually some people are looking at it, but it's also an extremely difficult problem. It already starts with like, what is the definition of fair in the case of regression? And so let's see how I can do this.
Would you like to share your screen again?
Yeah.
Great.
So can you see my? Voila, can you see the whiteboard?
We do.
Okay, and so suppose, and the thing we want to predict is the salary that someone should receive. And so we have our data, and it's our predictions. And so we have our salaries. And suppose that the distribution of the salaries of males is like this, and the salaries of females is like this, and then this is clearly discrimination because they have a different distribution. However, and now suppose that we add just a few examples here of we just add 2 or 3 females that have a very high salary, then it could actually be that the mean of the salaries becomes the same. So we cannot use the mean in order to distinguish whether the salaries are whether it's discrimination or no discrimination. Another example, I suppose one group has salaries like this, while the other group it's much more concentrated. It's like this. Well, then it probably has to be higher. I'm sorry for my poor drawing skills. Is there discrimination here or not? And so one thing we could require is that the distributions are exactly equal. We could make some kind of quantile plots where we compare if the distributions are more or less equal, but this tends to over constrain the algorithms, and so then it becomes really difficult to make a fair decision. So I would say there are people looking into this, but at the moment progress is actually rather limited, exactly because of this problem of defining what is fair in this regression context.
Great. And just want to let people know that we were looking at some bell curves, basically some fairly normal distributions for the most part, and how they overlapped in different ways, and that the sort of the middle can be misrepresented as being the same depending on how the model is, how high it is in the center, etc. So just for people wanting to know, it was looking at those distributions. Mm-hmm. I just wanted to describe it. I didn't want to interrupt when you were just drawing it. So we also have a question. I don't know if you're able to look at the Q&A queue to see what interests you there. We have a question around variance and how variance affects the output behavior, or differentiating between bias and variance. Is that something that you're able to tackle here? Perhaps you need some clarification on that question.
Yeah, maybe a little bit like there is this bias variance decomposition, which is very well known in machine learning, where you can look at the difference between where you can trade in bias in your predictions for variance, but I don't know if it's actually related to that issue.
Well, perhaps we can get the some further clarification from the person who asked it, and we can send it to you for a look-see after, or perhaps we'll be able to answer it within our own team. And I'm going to just do one last question because I am conscious of the fact that we're over time, but the rest of the questions will not be forgotten. We'll make sure that we try to address them after the fact. So there was a question around gender-neutral language and how models fare when it comes to gender-neutral pronouns and terms. Is this something that has an impact on those machine learning models that you were discussing a little bit earlier?
Yeah. So I'm sorry, I lost the question a little bit. So it's about gender-neutral language, yeah? Yes,
I think this was referring to the was it WordVec, where those where there were relationships. It was sort of the he/she kind of comparisons and putting vectors between those words, but we use there are many more neutral pronouns now that we're using that aren't masculine, feminine, or aren't necessarily attributable to male or female qualities. And does that have an impact? And maybe we haven't looked into that, or it doesn't quite fit.
Well, I can imagine if society is evolving and we start using different pronouns, that the models that are trained from on this type of data will also become different and will become less biased. And if the input data society is becoming less biased, resulting in less biased data, then our algorithms will also become less biased. So there is definitely an effect there. Now, but basically, if you want to do this type of general neutral representations, then what you want to have is that the vectors that you're giving to he or to she, and that they are actually being given the same vectors. So that is where the difference is laying. So if someone is, then it doesn't matter anymore if someone is using he or she or a neutral pronoun, and then basically the algorithm should be make a representation that no longer allows you to distinguish between them. I don't know if this answers more or less the question. So yes, if people are starting to use some more general neutral words, this will have an impact on the training data and hence on the representations that are learned on the data. But that is not the initial goal of the research right now of making the representation gender neutral.
And you obviously also have the redlining issue, or the equivalent of the redlining issue, in that not only do you need to eliminate the use of the gender terms, but the associated text.
Mm-hmm. Yeah, absolutely. Yeah, that's a very true remark.
Well, I'm going to regretfully close our webinar now. We have more questions. I promise we'll do our best to address all those questions and post them on the website. We'll send you a follow-up email, everybody, to let you know when things are on the website. And thank you again, Dr. Calders, for joining us. Really enjoyed your presentation. And I think it was a great start to our events that will be working towards learning and sharing and co-creating around topics related particularly to machine learning and ethics and other things like that, as well as other topics